Okay, thank you very much for having me at the Australian Space Research Conference in 2019. I'd firstly like to have my regards to the traditional owners of the land people. And again, I guess I'd like to start off as well, just saying that I'm not going to be too heavy on the figure side of things. I'd like to talk a little more briefly in the talk about what we actually mean by habitability, and perhaps sometimes the misnomer that habitability actually is. What I really enjoyed about this particular project is that by going and actually finding, getting the ability to actually model the top of an atmosphere and how much radiation is hitting the top of an atmosphere, that we can actually start to get an idea of the climate of a potential planet. Now, people have been trying to work out climate models for a long time, and it's often an area, even in the mainstream at the moment, where people are sort of stating, oh, do we really understand how much radiation is hitting the tops of atmospheres, and do we really understand our own global climate models? So I guess what I wanted to do is to go back and create a Python programming model which would map the radiation hitting the top of an atmosphere according to the position of the planet with respect to the star, how much it was tilted, which we sometimes call the axis of tilt or the obliquity, as well as the phase, or whereabouts it is in its orbit. So planets, obviously, as you can see from the next slide here, we understand that obviously our Earth is obviously circling around its star, and we have an aphelion and a perihelion, and that actual travel is the actual phase. So there's at differing amounts of like the seasons, we actually have a different amount of obviously daylight, which is obviously the hitting the actual planet. So this makes be mapped quite accurately, and we can start to build up what we call flux maps. So incident flux maps are actually useful because they give us an idea of how much energy is actually coming into and hitting the top of a planet. And only by having those accurate models can we then start to go beyond that and look at more accurately modelling the actual climate on a planet. Now we're at an exciting time here in terrestrial exoplanetary science, because now we're finally coming across some really interesting planet candidates, terrestrial planets, which we're able to do potential follow-up studies. And as has already been mentioned by previous speakers, with advances in the technology and the resolution of space-based telescopes, in addition to being able to do follow-up on the ground, we're now able to find a whole subset of terrestrial exoplanets as opposed to the hot Jupiters that Graham was just mentioning. So what I actually really find interesting about looking at terrestrials is that terrestrials are more ones like the ones that we know. So we know the terrestrial planets being Mercury, Venus, Earth, and Mars. What makes these planets special? How can we accurately use models to actually map perhaps other planets around other stars that could perhaps potentially exhibit factors that might make them habitable? And as you can see here, there actually are a number of factors that I'll go into. What I wanted to just briefly hit you with here is, yes, it's a whole lot of text, but what it is it shows you there's actually not that many terrestrial exoplanets that both satisfy mass as well as actual exact size. And what I mean by that is if we take transit and radial velocity data and we find out what we have both of both, then there's only a much smaller subset of planets that we would regard then as being terrestrial candidates that we can then do flux maps on. But it is going to be an area of growth in terms of the number of planets that we discovered, and of course the pushes on to find planets, of course, which might exist in the habitable zone. Now, habitable zone can be considered fairly optimistically, and the word is actually fairly loaded. That we're talking here is the optimistic habitable zone, you can see which extends all the way across, or the conservative habitable zone. And you can see that even Venus is just outside that zone, obviously the runaway greenhouse effect, which is certainly happening there. The model that I've created is not this one here, this is an animation to do with TRAPPIST-1, but the TRAPPIST-1 system certainly captures a lot of people's imagination, and we do creating some flux maps of the respective planets in that system. to perhaps be able to sort of add to the conversation about, let's try and use these flux maps, or these maps of radiation on these planets to sort of say, what would they be like if they had particular tilts? So the tilt of the Earth is 23.5 degrees, which gives it its seasons. So if we were able to consider, these what we call habitable zone troposphere planets, what might they look like based on particular tilts? Now the modelling that I did was based on some work previously from Kane and Torres, but what I had to do is go back and actually create a Python program model independently and then be able to validate that model from Kane and Torres. So I bring it again back to our own solar system because I like to bring back the work that we're doing in exoplanetary science to always looking at how that relates to our terrestrial planets. And as you can see here, we've got Mars, Earth in that habitable zone. Now, of course, with Venus inside. Also, I'd like you to draw some attention here to Mars. Mars actually has a fairly interesting orbit there. You can see that it's at some stages quite sort of a lot closer to its habitable zone there, so the way that's bunched across a little bit there. The first one I'm going to look at is Kepler 186f. And this, if you don't know what Kepler 186f is, it's a larger planet from Earth, as you can see from the picture here. It is resident in its in the habitable zone of the planet. When I say habitable zone, I say in an area where potentially, if liquid water could potentially exist on the surface, which of course would be dependent on having the right atmospheric pressures and so forth to be able to have that happen, then yes, it could be considered to be perhaps a promising candidate for at least further follow-up. Okay, so finally, flux maps. I promised some flux maps. Here's one that I've created. This is for 20 degrees of tilt, which is obliquity, for Kepler 186f. And I created this one because I really wanted to validate the model according to the model by Kane and Torres. I'm going to flick ahead a couple of slides and come back to this one, because I want to show you now Kane and Torres' work. You can see the top picture there actually indicates the same amount of obliquity there, which is 20 degrees. So about 20 degrees, as you can see, what that red means, and the blue is, the red is, imagine that's the area of the hottest part of the planet, and the blue is the cold. As you can see, in the middle it's 50 degrees and then 80 at the bottom. So what I'm saying here is that the more you tilt a planet in terms of giving it its obliquity, and the more extreme you make that, the more challenging it potentially can be to get a favourable flux situation that gives you a climate which you might regard as being more favourable, more likely to potentially have life. Remember, habitability is a very loaded term, and so I use it with caution. So the overall terms, the project, I wanted to look at these flux maps and create them for a number of the exoplanet targets that I chose. Also, not to say that there are other opportunities potentially to find exoplanets that could potentially have life, such as exomoons. And the flux maps here, when they're actually utilised, they can be a tool. They're not the be-all end-all. They are literally just a tool that we will be able to use to perhaps be able to validate and to provide us with some additional input. So I'd like to just draw attention. I will be publishing my work in hopefully the monthly notices of Royal Astronomical Society. So please stay tuned for that. If you'd like to connect with me, I am on LinkedIn and on Educating Space. I mentioned the Educating Space one because I'm doing some animations to do with what we actually talk about when we talk about planets and tilt and so forth. And I find that's a useful tool to actually be able to sort of communicate that in a much more visual way using Instagram. And then I'll be actually posting on the post from there and drawing it into the research that I'm doing. So I hope that you have enjoyed my talk. And this is just one of the animations that sort of I will get you to go and have a look at if you do have Instagram. It'll give you a much better idea if you are explaining what we mean by obliquity to people. So feel free to go and I would like to welcome any questions.
Thank you for not even keeping to time, but under time. So we have time for questions. Let's go for it.
Can you put it back on the last slide?
The animation.
The animation that's over to get it.
Yeah, so this is an animation from Educating Space. So I've had permission from James O'Donoghue from NASA to use the animations. I believe that he has. The animation here, when it's actually playing, shows you the various axial tilts or obliquities of the different planets. It also shows you how fast those planets are actually spinning as well.
Can't play.
I won't hit play on this. I'm going to encourage you to go to the Instagram page where you can see it in your stories. Yes.
So you're obviously using some underlying models in your programming, so you're wrapping some models in your
Yeah, absolutely. So
what are you actually using?
So the models, so it's a Python program that I've used based on Kepler physics to accurately map the radiation hitting the top of an atmosphere, and then the way that that's been mapped has been an iterative process.
So it's not like a global climate models?
No, so remember it's like to stress, it's hitting the top of the atmosphere, so it doesn't actually, it's then something that then can be fed into a GCM, a global climate model. Yes?
So earlier from Jonty's talking planets, that some of them don't have some really wacky orbits and how fast they're spinning around the sun. You said that some of those ones in that habitable zone.
Yeah, I'll go into the slide.
Support the difference in heating and cooling, but with that rapid spin that they've got going on, does that make a massive influence?
It could. So in terms of the rate of spin of a planet, it's still going to be exposed to radiation regardless of how fast necessarily the planet is individually spinning, and the rate of the Earth's spin has changed over a long period of time. I guess maybe perhaps what is more of significance is the obliquity. So the obliquity when we actually, so imagine the Earth instead of having 23.5 degrees tilt, imagine it had say closer to 90 degrees tilt, and what that would actually look like. So that's what I hope to show in the research that I do, and show you that potentially that would lead to areas of that planet which would be devoid of flux for fairly long periods of time, which would of course then impact on their climates. But even just going from small levels of change from 23.5 degrees, you see it can quite drastically change the radiative flux.
If I could jump in for a moment, scientifically, that if a planet is in a very close orbit, it'll be tidally locked like the moon is around the Earth. And so what's interesting is the insulation will be cooking on part of the planet perpetually, and that's when you start to invoke the global climate models and see what sort of climate you get from this perpetual heating on one side and nothing on the other. And that's where it gets interesting from my point of view. There was another question up the back, I think.
Yeah, I wonder if the role of obliquity in creating seasons, if that's an important driver of evolutionary processes. So there could be a kind of optimal point of obliquity where you get sufficient variation to drive biological adaptation.
Yeah.
Not too much that creates uninhabitable regions.
I'm glad you brought that up, because with our own Earth, we have Milankovitch cycles, which means that tilt of the Earth from 23.5 degrees actually varies over sort of over the cycles of time. And actually, if you have a look at Professor Jonty Horner's poster, which is just outside, it does discuss Milankovitch cycles more.
I was just going to chip in on that as well. It's an interesting thing that as you get more and more eccentricity actually drives eccentricity-driven seasons once it gets big enough to overwhelm the inclination element of it. So if you've got a really eccentric orbit, you get seasons that are driven by the shape of the orbit, not by the tilt of the planet's axis. And a lot of people get that wrong the other way around. I've heard primary school teachers say that the Earth is hotter in summer because it's nearer the sun. And that isn't true on the Earth, but it is true on planets around other stars. You do get some places where the seasons are driven by the eccentricity, not by the tilt.
At that point, we will move on, and thank you once more, James.